you can observe this kind of scenario. Another evidence is from called gravitational lensing, which is basically bending of light, as we know quite well, by the distortion of the space-time. So if you have a galaxies or any source, and then you are trying to see in the Earth. So if you have a common like a lens, in case of lens, it's kind of changes its path from their usual way, and then if we try to see the image, you see in the different position. So that's what it happens in case of galaxies. So we have a bigger mass or cluster of galaxies which has mass which we cannot see. Now the only explanation, so if you have a distant galaxy and trying to see the galaxies from Earth, we see the virtual image of the galaxy is not at the right position. So only explanation can be, one of the explanation can be that the light what we are seeing from the galaxies are distorted by the space-time. That can only happen if you have a very large mass of the stars, of the other materials. That means there are some extra matters that we are not able to observe, which we call, as we are not able to see those, we call as a dark matter. Which are the particles is the dark matter? So that's kind of give you the motivation to understand why you are looking for the dark matter. But our concern will be to understand, as a particle physicist, to understand the particle nature of the dark matter, because that's what we understand at the laboratory, at the detector. We're trying to find out the footprint of the particle in our detector. When a particle goes through the detector, it gives you a lot of information, like if it is charged, energy, momentum, everything, and that's what we try to reconstruct them and try to find out the particle exact nature of the particle. So what kind of particle is this dark matter? So there are a couple of possibilities. What can be axion, can be WIMP, can be neutrino, all of this. But here I'm not going to talk about that in detail for the different one, but one of the possibility is that we don't know much about it. So one of the leading candidate is the WIMP, weakly interacting massive particle. So far we understand about the dark matter, as we already talked. It's not luminous, obvious. It's dark. Otherwise we could have seen it. It's not a short light. Otherwise we could have so the ratio of the dark matter to the standard model right now from the beginning of the Big Bang, we see is kind of the constant. So if it is short life, if it would have decayed, we would not have seen that kind of ratio. And it's not hot, it's a cold, because from different examples, like from the large scale structure, we see to form our universe, it needs to be cold. And obviously, it's not a strongly interacting particle. Otherwise, we have seen the particles which interact strongly. We could have detected it long time back. So it's not then within the elementary particle physics in that list. It belongs. So we need to go beyond the standard model of understanding of particle physics. So we need to go to the beyond a standard model physics. What about the neutrinos? We all heard about neutrinos in remaining lectures, so I'm not going through detail about it, but just to completeness. So neutrinos, we know these are the neutral electrons and only interacts via weak force. There are three flavors which are experimentally detected: electron neutrino nu e, muon neutrino nu mu, and tau neutrino nu tau. And also experimentally, we have observed neutrino oscillation from different experiments. So neutrinos oscillate from one flavor to the another flavor, and one of the most scenario to explain or the phenomenology to explain the neutrino mass, the neutrino oscillation, is to bring the neutrino mass. And then that's the question. So within the standard model of particle physics, neutrinos cannot have mass. So standard model cannot explain the existence of neutrino mass. So we need to go beyond the standard model in case of neutrinos as well. So what are the synergies between the neutrinos and the dark matter in this case? Well, so for the dark matter, phenomenology is now turning to a more exotic models, because we are trying to understand the particle nature of the detector with different kind of phenomenological model, and then if we don't see, we change the model, and so it's going to be a more kind of exotic different models we are trying to test inside the detector, and neutrino detectors are now sensitive to some of those. So we can use the dark. So my talk will be focused on mostly having that fill in that using the neutrino detectors. What can I do both for the neutrino as well as the dark matter? On the other hand, I'll try to, at the end, I try to give you a brief motivation about the, as well as the dark matter detectors also becoming very high resolution, low threshold, and more sensitive. So they start to have something about the neutrinos as well, not only about the neutrino oscillation, but other kind of neutrino scenarios as well. So let's first talk about the neutrino detection and what neutrino detectors can do for the dark matter. So as we know that neutrinos are very elusive, very, very weakly interacting particle. It's making experimentalist or experimental inquiry of neutrinos a very, very tough. So for detecting the neutrinos, we need a very massive detector with a very good understanding about the signal and the background. So the key point for the neutrino detection is to have a very large mass, and you would expect a full clear image of the interaction that you see inside your detector. So you have to build your detector so that so the detector is so sensitive with the minimum background and improving the resolutions with a larger bigger scale, like with a larger bigger scale, but the image quality will be like a bubble chamber, where it shows that we can clearly see the tracks from the different particles from the neutrino interactions. It's one of the pictures taken from the bubble chamber. But with the but for the neutrinos, you have to scale it. You have to have a very large detector because the cross section is very low, and you have to have a very fast readout because you do not want to miss any signal. And obviously it should not be very expensive, otherwise you cannot build such big kind of detector. So are there any such kind of technology? Yes, one of the possibilities to have a liquid argon time projection chamber. So it's a kind of new technology in the sense of particle physics detector R&D, and it's for the new kind of discoveries that we are expecting. So the journey started for the development of the liquid argon time projection chamber, or the large TPC call for the neutrino physics, starting from 1970s. The concept from the bubble chamber at CERN, and right now, and then up to the bigger scale, the first liquid argon TPC built at Icarus in 2010 at Gran Sasso laboratory. So it's kind of, so you have we have a gaseous TPC. So the liquid argon time projection chamber is kind of successful marriage between the gas argon TPC with the liquid argon calorimetry. So that we can obtain clear picture of the interaction that we want, means you have to have a very good tracking of the particle, all the 3D informations of the interactions. You would have excellent particle identification, means what are the daughter particles after your interactions happens inside the detector. You should identify that very well, and then as well as you have to measure the energy of the incoming particle for the neutrinos with very precisely. Just quickly remind you about the history for the liquid argon TPC. The concept built by Carl Rubia in 1977. It's using the concept of time projection chamber from David Nygren, and in 1974. And then in this paper, he described how give the motivations and the idea to develop the large scale or the first liquid argon time projection chamber. Okay, now I just go quickly about the understanding of how this liquid argon time projection chamber works for any particle. Let's start with the neutrino. That can be any charged particle as well, but here we are interested for the neutrino. So when you have a neutrinos hitting the liquid argon TPC, means inside the detector you have active material as the argon. It interacts with the argon, produces both ionization and the scintillation light. So the ionization produces electrons, and then we apply the electric field, which basically drifts the electron towards the readout plane. So readout plane in case of liquid argon TPC for kind of one of the, I'll call later, we call single phase liquid argon TPC, is the wire plane. So we place 3 different wire planes in 3 different directions. Mostly one is collection, one in induction plane, and then basically, or you can call as the anode plane. Then those electrons which are drifted are finally collected by the anode. So that gives you the ionization signal. And then later, and then when simultaneously the charged particle of the neutrinos produces the scintillation light, then scintillation light mainly produces photons, and those photons are detected by the photomultiplier tubes, the PMTs. So then from the anode, you get the signals on the wires. You read that out from using your electronics, reconstruct that, get the heat information, reconstruct the track, you get the image of the track, and from the photomultiplier tube, you get the timing informations of that interaction happens inside the detector. So you have a clear picture of the interactions. You have both the coordinate where the interaction happens, as well as the timing informations of the event. So why we choose the liquid argon? Why not other material? Because we know that liquid argon or the argon is a noble element. The key feature of the argon is that it doesn't attach to the electron. It basically, so that means you have a long drift which is inside the liquid phase, and then the absorptions of the electron is very minimum. Then you have a high electron mobility compared to the other noble elements, but except the helium and the neon. So this table shows comparison of the different noble elements. You can see the argon is kind of the leading candidate, in the sense that scintillation light is also very large with minimum attachment of the electron inside the liquid argon, and also it can be made very pure, and the impurities will be very less, because that is one of the concerns for detecting any this kind of process, which are the rarest process we can call, because the interaction is very less. So you have to have a very pure kind of active material inside your detector. And another the best thing is that the liquid argon is opaque to its own scintillator line. Means it doesn't absorb the scintillation light itself when after the interaction happens. And obviously we choose the liquid phase because of high density, so you have a very large cross section, and then it's possible to produce the homogeneity and uniformity across the long drift volume for the production of the large amount of ionization electrons inside the detector. Just give you a picture about how this imaging and the energy reconstruction happens inside the liquid argon. As I already talked about, there are mainly 2 planes we call collection and the induction plane, and you have a time coordinate which we get from the photomultiplier tube or any light detection system detecting the scintillation light. So when particle interacts, you have produces heat coordinates. So you have a kind of 2D informations both on the collection and the induction plane, and then you have a timing coordinate, so that you get the clear z coordinate, and so you have a 3D image in that sense. So, and then from the heat amplitude, what we collect at the anode plane, we convert that heat amplitude to the to the charge dq charge deposited inside the wires, and then we know how far that heat how far that particle travels, or in terms of heat distribution, you get number of space point or you call it as a track pitch, dx. So then you convert that charge deposited to the energy deposited with some factors, and then you plot the energy loss. Basically, that's what you get the energy loss inside the detector. You plot the energy loss of the particle inside the liquid argon. And then if you plot the energy loss, that will give you the particle ID, which I'm going to talk in the next slide in detail. And then when you integrate over the energy loss over the track length, the particle traverse will give you the particle energy or the calorimetry of the particle. That's also information that we need from the interaction point of view. Yeah, so this is about how we get the particle ID and the calorimetry. So as we talked in the previous slide, so you have a 3D clear image of the particle interactions, which has a very good spatial resolutions of the order of a millimeter cube. So we get the integral heat of the of all the heats that inside the detector, and get the energy deposited on the DDX as a function of the distance it travel for the different particles. So if you plot it, the massive particle which are heavier will give you a more energy loss because of the Bethe-Bloch formula. That's what then you can clearly identify the particle ID, which particle it is, from the energy loss inside the detector. But there are other factors. When you calculate from the charge deposited to the energy, there are also factors of recombinations and other factors necessary, which I'm not going through that in detail. Okay, now to talk about little bit about the scintillation light, in how this happens in a bigger picture. So when you have any particle like neutrinos, any charged particle, here it shows proton, hits the argon atom, transfer the argon, both and ionizes the argon. So the argon produces ionization, as well as as it gets the energy from the particle, it goes to the excited states. So that's called the atomic excitation, and then it does the self trapping with the nearest argon atoms, and then it decays with the radiative decay. Basically, it goes to the, so there are two different kind of states, which called the singlet state and the triplet state. So it basically, when it jumps from the excited to the ground state, it emits the scintillation light. So from the singlet state to the ground state is the fastest component. We call it the self-trap luminance is of the order of 6 nanoseconds. And then you have a decayed product, which is kind of later. We call the a slow component, which is 1.5 microsecond of the order. So in case of liquid argon, the yield or the number of photoelectrons produced by the inside the liquid argon is around 40,000 per MeV, and then it produces the scintillation light of the order of 128 nanometer, which is not in the visible range. So we have to transfer that energy to the visible range, so that the photomultiplier tube which you have can basically detect that and then gives you the signal. So that's why we use the wavelength shifter. Basically, you do a coating which basically transfer the wavelength, one wavelength to the another wavelength. It basically changing the energy from one to another, and then you get the longer wavelength scale. And as I already talked about, it's the best thing about the liquid argon is it's transparent to its own scintillation light. So there is no absorption of the scintillation light inside the liquid argon. And then finally, the signals are recorded by the photomultiplier tube, and this will give in kind of beam experiment that will start as a trigger. So that's, you start as you're collecting your readout signal from the detector. Just to give you an overall picture about so far liquid argon TPC detector builds. So as I already talked about, the Icarus is the first biggest scale liquid argon TPC build in the world. It's first built in Gran Sasso laboratory It's 476 tons of active mass with more than 50,000 of wires with 3 different plates. So all the features, as I already talked about, are there with the photomultiplier tube, and it started taking data from 2010 to 2013 at underground. It basically looked at it took data almost for 3 years, and did a fantastic job in terms of understanding the liquid argon technology. And then there are simultaneously there are small scale R&D going on in US, like in Argonet, one of the experiment, tabletop experiment, very small scale liquid argon TPC of the order of 240 kilogram of active mass with a smaller number of wire plane, but it started taking data in 2009 for almost 2 years, which also gives a very good understanding about the cross sections, because it placed in very close to the neutrino beam, which gives understanding about the neutrino cross section quite in the 1 to 10 GeV region. And then right now, the bigger picture, the microboon is kind of bigger than Argonet, 87 tons of active mass with 3 different wire planes, and it's also started taking data from 2016 and currently taking data, and the physics motivation I'm going to talk about later. So now, so for the whatever we have right now, and to go beyond in future, the planned experiment for the neutrino physics with the liquid argon TPC is called short baseline neutrino experiment, which having 3 different detectors. Both are liquid argon TPC in neutrino beam at Fermilab. One of the detector 3 combinations are microboon, a short baseline near detector SBND, and Icarus imaging cosmic ray underground that was in Grand Sasso, now moved back to Fermilab to have all these 3 detectors in a place to understand about whether we have sterile neutrino or not. And then the bigger picture is DUNE, deep underground neutrino experiment, which tries to understand about the neutrino oscillations, CP violations, and nuclear decay, and other so many beyond standard model physics phenomena, which I'll go in detail about. So deep underground neutrino experiment, or the DUNE, is the leading edge international project for understanding about the neutrino science and the proton decay. So the main point is it's a long baseline neutrino oscillation experiment. It's going to use most intense neutrino beam, means so far we don't have, it will use 120 GeV of proton energy with 1.2 megawatt of beam with a bigger 40 kiloton liquid argon TPC with 4 10 kiloton modules, and with the excellent near detector, all will be mostly liquid argon TPC technology. And so the beam will be from Fermilab, and the detector will be located at Sanford Underground Research Facility at about 1.5 kilometer underground. So the primary physics motivation, as it's built for the neutrino oscillation experiments, obviously to understand the neutrino oscillations, mostly the mass hierarchy, measuring of delta CP, and finding out the exact value of θ23 or the θ23 octant, and other physics like the physics beyond standard model, which I'm really interested of now, and nucleon decay, supernova burst neutrinos, and so on. But before building that bigger kind of like 10 kiloton liquid argon TPC, DUNE proposed to design a prototype detector called Proto-DUNE single phase liquid argon TPC and Proto-DUNE dual phase liquid argon TPC. So about the beam that DUNE is going to have is called long baseline neutrino facility. It is going to have a most intense neutrino beam around 120 GeV at Fermilab from main injector, with the initial power of 1.2 megawatt, and will be upgraded to 2.4 megawatt. So it will have a wide band of region of energy, so that we can cover all kind of sorts of beyond standard model physics phenomena. We'll have a muon neutrino and antineutrino from the beam. Just go quickly about the FAR detector. As I already talked about, it will have both, all four will be liquid argon TPC technology, with single phase, as I already explained about single phase and the dual phase. I'll talk about dual phase a little bit in a while. So this is kind of dimension of the liquid argon TPC that 10 kiloton module will be. It will be a very a kind of gigantic module of liquid argon TPC. It will also have a near detector with composed of multi-purpose with different kind of detector. Called one of the most important one will be liquid argon or the argon cube with the following dimension, and then there will be multi-purpose detector to understand and about the muon spectrometry and so on. And then there will be a sand detector which will provide the on-axis monitoring of the neutrino beam and the rate very well. So this is kind of overall picture of the near detector that DUNE is going to have. Now, go quickly about the Proto-DUNE single phase. So Proto-DUNE prototype at CERN will have the Proto-DUNE single phase and Proto-DUNE dual phase. So this shows the Proto-DUNE single phase detector, which already took data maybe more than a year now, and a Proto-DUNE dual phase. It's basically taking data, not under. It's basically taking data now, mainly the cosmic. So let's try to understand about why. So we talked about the single phase liquid argon TPC so far, but why do we need the other liquid argon TPC technique, which is called the dual phase, or we call the double phase liquid argon TPC? So as we all know or talked about that, neutrino experiments requires a massive detector, right? Because the cross section is very low, you need to have a very long drips or very large volume, So when you have a very large volume, you will have a very long drips of the electron. So there is a possibility, if the liquid argon or any material is not pure, active material is not highly pure, there will be a charge attenuation. So you will miss a lot of signals where if there is the material is not ultra pure. So there is a possibility of having charge attenuation. So you need to have a amplifications of the signal that you are getting inside your detector. In case of single phase liquid argon TPC, there is no provision of having charge amplifications for inside the detector. So that's the main concept of having the dual phase liquid argon TPC. So you have this concept basically have, so interaction happens inside the liquid volume, and then we extract that signal or the electrons or the ionizations from the liquid phase to the gaseous phase, and we do the multiplications and then finally collected by the anode. So we basically do the amplification of the signal so that we don't lose the signal if for a longer drift of the detector. So the main features for the dual phase is to have a amplification of the signal so that we have a very large signal over background ratio. To compare apple to apple between the single phase to the dual phase. So single phase is basically, so all the interactions, collections of the charge happens inside the liquid media, inside the liquid argon. So the liquid argon, the wire planes or the anode planes, you call anode planes, are also immersed inside the liquid. So everything happens inside the liquid medium. But in case of dual phase, interactions or the ionizations happens inside the liquid. Then we apply the extraction grid, which extract the ionizations from the liquid phase to the gaseous phase, where we will have a large electron multiplier, where it basically multiplies the signal like gas electron multiplier GEM. And basically then those are collected by the anode readout plane. So the main difference is that in single phase, there is no amplification, but in dual phase, we have the amplifications of the signal. Just to give you overview in better way, so we have extractions of the ionization happens inside the liquid phase, extract that using the extraction grid, which immerse both in the liquid and the gas phase, extract that to the gas phase, and we have a lame which basically multiplies and finally collected the charge in using the anode plane. Okay, now start talking about, so that's overall about the neutrino about the detecting the neutrinos using the liquid argon TPC. So now about the neutrino oscillations. So for the remaining, for the last few lectures, I think you already have a detailed picture about the neutrino oscillations, but to give you a overview about the neutrino oscillations. So the neutrinos, as we know, that we have three different flavors: electron neutrino, muon neutrino, and tau neutrino. And these are those muon neutrino, or those flavor neutrinos are in superpositions of the three mass eigenstates of the neutrinos. That's we call 1, 2, and 3. So the flavor of the neutrinos are the fractional of the mass basis of the neutrinos. So there are kind of two pictures that we have. Either the mass eigenstate 3 will be higher compared to the 2 and 1, or otherwise inverted one, it's either 3 will be less than 2 and 1. So we don't know that about that. That's we call the mass hierarchy. Okay, so we need to understand whether this picture normal ordering is there, or whether this picture inverted ordering is there. And then this mixings about the mixings between the flavor to the mass eigenstate with the coefficients, we got the mixing matrix, which is called the QPMNS, which contains all of this mixing angle theta 2, 3, theta 1, 2, theta 1, 3, and the delta CP, which the mixing matrix, the mixing angles we have measured, and the delta m squared to 1. Basically, the solar delta m squared we have measured experimentally so far with great precision, but we need to measure the remaining questions like the mass hierarchy and the delta CP. So the key questions about the neutrino physics or the neutrino in terms of neutrino oscillations is understanding about the neutrino oscillation, as I talked about, whether it's a normal or the inverted ordering. And then we need to understanding about the CP violation. Because antineutrinos are same or they are different. In other words, delta CP is 0 or pi, is different from 0 or pi. As well as we don't know because one of the neutrino oscillation probability depends on sine square 2 theta 1 3 from few channels. We cannot really calculate the exact value of theta 2 3, whether it's maximal or not maximal. And then we need to do a precise measurement of the oscillation parameters. To talk about understanding about the CP phase, and mostly for the DUNE, which is looking for one of the important channel is called a NUE appearance from nu mu beam. So the probability of nu mu going to nu e in 3 favor is kind of it depends on, as you all already talked about in the previous slide, of the coefficients like the mixing angles theta 2 3 theta 1 3 delta m squared and the delta CP. So the larger values of currently measurement of larger values of sine square 2 theta 1 3 provides significant nu events, which will give us a better understanding about the measurement of the mass hierarchy. So the appearance channel basically depends upon all the mixings as well as the delta CP. So if we measure the appearance channel from nu mu to nu e, we can calculate the mixing parameters and as well as the delta CP, and obviously the mass hierarchy using the matter effect, and then from the disappearance channel we can measure the theta 2 3 exact value whether it's maximal or non-maximal. Just give you about the big results of the or expected results from DUNE in terms of CP violations sensitivity. Obviously, this is a simulation, not because DUNE is not taking data. But this gives you the sensitivity to which DUNE can talk about whether CP is delta CP is 0 or pi, or how far it deviates from the delta CP phase from 0 to pi as a function of delta CP. So in case of 7 years of data, so this is with the a normal mass ordering. So with 5 years of data with DUNE can talk more than 3 sigma, almost for 50% coverage of delta CP space for a normal mass ordering scenario. About the mass hierarchy, so the sensitivity to determination for whether normal ordering is there or the inverted ordering is there, DUNE can talk about more than 5 sigma sensitivity with more than 7 years of data taking for almost all region of delta CP space. So within maybe less than 5 years of data, DUNE can talk about more than 5 sigma for hierarchy. Hierarchy can be resolved quickly compared to the delta CP1. Okay, now go to the another plant liquid argon TPC, like as I talked about the short baseline neutrino experiment, which is designed at Fermilab to understand about the existence of sterile neutrino or not. So what is that about the sterile neutrino? Why we are looking for, why we are trying to understand that? Because last 20 years, there are a lot of short baseline experimental anomalies that we have seen. Here, the left hand, this shows the event spectrum from the one of the earlier experiment called LSND, which sees excess of event in the lower energies, which doesn't explain the neutrino oscillation that the detector is designed for. And then Minibun is designed to understanding about the LSND anomaly, whether with the same L over E region. So LSND sees an excess of 3.8 sigma in the lower region, and then Minibun later designed with to understand that anomaly with different kind of detector, but with the same L over E, because that's what it matters. In the neutrino oscillation, you have L over E. That's you basically vary incrementally. So if you have a L over E same, whatever the detector be it is, the physics you try to get should be the same. Then interestingly, Minibun has seen excess of events at the lower energies, but not exactly at the same energy that LSND has seen, but more like as LSND has seen in 3.8 sigma, it has seen like 4.7 sigma excess in the lower energies. And then simultaneously, there are reactor anomalies recently. They are trying to improve the calculation of the nuclear matrix elements, and so on, try to find out the flux from the reactor. They have also seen excess of events. So there are kind of clearly there is something going on which we do not understand, because the standard neutrino oscillation cannot explain those excess of event for those kind of scenarios. So we need a dedicated experiments to understand that anomalies. So to avoid that, we the SBN, the short baseline neutrino program, plan to place 3 different detectors to minimize the systematic uncertainties, so that we understand the detector very well, and whatever we are seeing in that the detector cannot be explained by, cannot be mimicked by any kind of detector systematics or uncertainties. So that's why SBN is proposed to have 3 different detectors. One called very near to the booster neutrino beam is called SBND. Then microbone is already located at 470 meters from the beam, and then Icarus detector is placed at around 600 meters from beam, which I already talked about. So its main motivation to understand about the sterile neutrino, and then we can use the same experimental setup to look for the dark matter, which I'm going to talk later. So as I already talked about the Icarus, it's right now at Fermilab at the SBN program, and it's going through a lot of changes before it plays at Fermilab. I'm going to skip, I already talked about, and right now it's all the detector component installation completed, and it started cooling down and filling the liquid argon, and we are already done with the filling, and we are expected to start taking data very soon. Okay, just to give you about the simulation results about the SBN to talk about the sterile neutrinos. This shows the left hand from the appearance channel, the right hand plot is from the disappearance channel. both basically you try to understand about the mixing and the delta and square if you have a one extra sterile. So SBN can cover more than 99% control level with 5 sigma, just 3 years of data, and the new mu disappearance with the appearance channel will confirm if there is any excess of new in that LSMD and the mini boon experiment has seen. Okay, so that's so far about the neutrinos, that neutrino physics with the liquid argon TPC. Now, the another, as my talk title talk about the dark matter, is what we can do with those neutrino detectors to detect the dark matter with dedicated kind of model. So you have a for accelerator based experiment or called fixed target experiment. You have a proton beam hits the target, produces the neutrinos, as well as you have different models which produces the dark matter, and then you detect using the neutrino setup or the neutrino detector to detect those neutrinos using the different channels. So what is the motivation for that to detect those dark matter using the neutrino detector? This is kind of a golden plot for the dark matter area or in the dark matter zone. So this is kind of cross section as a function of WIMP mass. So this shows the dotted line shows the limit from the direct detection experiment, or so it's kind of have a threshold at GeV. So, but you can go beyond. You can reduce the dark matter mass. You can go less than those limits. So we try to cover which have very good theoretical motivations to go beyond the WIMP mass below 1 GeVs, which we call a sub GeV region, and which are very, very well motivated by theoretical models. And using the accelerator-based fixed target experiment, we try to look for those kind of signatures using the neutrino detector. So just to give you a kind of cartoon picture of the image, how this interaction happens. So in case of standard neutrino interactions, you have a proton beam produces charged ion, decays to neutrinos, and then you basically detect those neutrinos using the neutrino detector. Okay, now we have everything set up ready for the neutrino. Now we can do the same kind of with different phenomenology, is that instead of neutrinos, you can have a kind of, the model kind of have a intermediate kind of vector photon, we call it dark photon, okay, which then finally decays to the dark matter, and then dark matter, basically then you detect those dark matter using the existing neutrino detector through different channel, like for the electron scattering and the nucleon scattering. And there can be different kind of models which produce the different kind of production models of those dark matter, both from the direct and as well as the decay from the mesons. So we can use the same kind of neutrino detector setup to detect the dark matter. So there are 3 kind of main experiments designed so far. One of them is called Miniboon, which already finished their data taking, analyzed their data with the booster neutrino beam with the mineral oil detector. So this is not the liquid argon TPC, but this was designed for the neutrino detection for the sterile neutrino. Then you have a SBN, Icarus, Microboon, and SBND. Then you have a DUNE detector, which will also be a liquid argon TPC. So we can use both SBN and the DUNE detector to explore the search for the dark matter. Just to give you about the understanding about the model, which called the vector, so-called vector portal model. This is kind of simplest model one could have in the sub GeV dark matter range. So there are kind of, it's basically you have a mixing between the standard model to the dark setter via this dark photon, which mixes with the kinetic mixing epsilon. So there are 4 free parameters. You have this the mediator mass, called MV, dark matter mass, and the kinetic mixing between the standard model and coupling between the dark photon and the dark matter. So that's kind of simplest model we are looking for the dark matter. I'm skipping this. This is kind of production mechanism, as already talked about, can be produced by direct production or can be produced by the meson decay. So these all are these all models are in a sense having the concept of proton or in sense that fixed target experiment kind of scenario, considering that. And the detection mechanism can be like the elastic scattering of the electrons, elastic scattering of nucleons, and deep elastic scattering. So the point is, the interaction of the scattering signature is kind of same as the neutrinos have. So there are a lot of similarities between the neutrinos. So I'll go through quickly about the mini-boon search, which has like which I already talked about. It's a dedicated experiment designed for the detection of the neutrinos, and then we use that for detecting the dark matter. So, and the mini-boon results we look for the beam dump experiment with charge measurements. We look for a signal which is beyond the beyond the data of the neutrinos. If you see beyond some background, that you call as a signal. So very good understanding about the neutrinos and the detector properties. They produce the results of the first fixed target experiment dark matter results, which is published in PRL. So this gives you the limit of the dark matter as a function of a kind of coupling parameter to the dark matter region. And then there are simulation results with the DUNE detector, as I talked about, using the setup that DUNE detector will have, and kind of constraints from the dark matter search on using the DUNE detector setup, which will also be important. And then we have a simulation results both from the short baseline NER detector, which also gives you the Icarus. Basically, this shows the Icarus, which is much better than some of the experiment which already analyzed the data. So there is a great possibility that Icarus detector will be suitable for light dark matter search. Okay, now I'll quickly cover before So what next? So far we talked about the detection of the detection of both neutrinos and dark matter using the neutrino detector. But we can reverse that. If we have a dark matter detector, that's the synergy. If you have a dark matter detector, very sensitive with low threshold, now you can use that setup for understanding of different kind of neutrino physics scenario. One of the called coherent elastic neutrino nuclear scattering, or we call CERNs. So the interaction is same kind of as the dark matter. Here, when a neutrino interacts with the nuclei, it's basically transfer the low momentum to the nuclei and scattered that, and then you get a very large cross section because the nuclear wave functions are in phase with the low momentum transfer. And only thing is that you get a very small kind of signature or very low tiny energy deposited, which has similarity like the dark matter direct detection experiment. This shows that dark matter, the cross section of the neutrinos in case of CERNs is very large compared to the other processes because of the coherence that you have in the nuclear wave functions. And so the main motivation is to, if you have designed your dark matter experiment, so this will be a very good background study for the dark matter detection, and this can be used for other BSM physics scenario, which I'm not going to talk about at the end. Okay, so how to measure is kind of same. You need to have a neutrino source. You need to have a precise understanding about the neutrino detector and with a low threshold. And then finally, the dual phase liquid argon TPC you can use for the detection of the CERNs or the coherent scattering, as well as for the dark matter search. Advantage is transparent to its own scintillation light and with high scintillation yield. And most importantly, it can discriminate between the nucleon and the electron recoil. If you look for the ionization of the scintillation ratio, then you can clearly distinguish between the electron and the nucleon recoil. That's the way you can clearly both discriminate the actual signal what you get from the dark matter, both from the dark matter as well as for the coherent scattering processes. But there are challenges you have to produce so that it can go to the very low threshold region. So finally, to conclude that liquid argon TPC are excellent detector for particle ID calorimetry, as well as the reconstruction of the events which are necessary for the neutrino physics and the beyond standard model of physics. DUNE is obviously the major neutrino experiment for understanding detailed picture of the neutrino physics, which will going to have a massive liquid argon TPC, as well as short baseline near detector will have a liquid argon TPC detector, which will try to understand about both the sterile neutrino as well as we look for the dark matter using the same setup. And then the accelerator based experiment, same kind of neutrino detector, are well motivated to look for the dark matter search. So in a way, and the dual phase liquid argon TPC can be used both for the dark matter search as well as other physics scenarios. So in a sense, liquid argon TPC can truly be a multi-messenger physics. Thank you.
Yeah. Thank you, Animesh, for excellent review of the entire Fermilab program on the short baseline neutrino physics detectors, and more particularly about the TPC technology and how it is going to stay there for not only for the current set of experiments, but also looking at other future standard, beyond standard model kind of physics to explore. And also you talked about, how it could be, especially the dual phase detector could be a great choice for futuristic, very low signal, indeed, these kind of experiments for the future, both at Fermilab and also at other places. I know you had to really wake up quite early to be in time at 6 p.m. for Indian time. I hope you're not too tired. Let's see if you have some questions that you can take up. Yeah, any questions to Animesh? There's one from Deepak. Yeah, Deepak, please go ahead.
Animesh, can you hear me?
Yes, sure.
Yeah, thank you for your nice talk. I have one question that you were talking about sevens, right?
Yeah.
So how do you distinguish a seven signal from a dark matter signal in your detector? What distinguishes these two?
What distinct? Okay, so basically, in case of sevens, like you are looking for a nuclear recoil, right? So yeah, okay. So basically is that, so you for sevens you have to have a kind of, if you have a like a neutrino beam, right? If you have a neutrino beam, then you can know when the beam is coming, right? So from there you can find out whether it's coming from the neutrino or not. And then it's kind of that's what, it's kind of exactly difficult to tell whether it's coming from dark matter or not. It's because that's why it's the major background for the dark matter search. But the only point, if you do a calculations of the cross sections, that will be different, right? So you have to analyze that. That's what I basically feel. But in other way, the kind of interaction point of view, that will be like the same.
Okay, so it's just the directionality that helps you finally.
Yes, mostly.
Okay.
Okay.
Because the process, as I said, it will be like the similar, almost like the similar, like the like the dark matter.
Because I've heard that there is in dark matter searches, they make that S1 to S2 correlations and all those stuff. Is there something there for the sevens also?
Yeah. So yeah, exactly. So if you look for the that's what you basically distinguish between the electron recoil to the nucleon recoil, right? You basically look the ionization of the scintillation ratio for the liquid argon. So this is very large. So if you look for like from the Neutrino experiment, but as I said, for the dark matter, you can have both electron as well as the nucleon scattering, right? So so it will basically it can give both the ionization and the scintillation signal. But the mostly if you have a like of, if you try to distinguish between your electron channel, if you focus with dark matter like only have a kind of nuclear recoil, right? Then you can clearly identify from the electron recoil very well by using this method, S1 by S2 correctly. If you do take the S1 by S2 ratio for two different channels like electron and the nuclear recoil, and then if you know that for the neutrinos, if this is your channel you are looking for, but you are looking the other process, then you can clearly differentiate between the two.
Thank you.
Okay. Yeah. Thanks. Okay. We have another one from Balasubramaniam KM. Just let me. Yeah. Can you unmute, please?
Yes. Am I audible?
Yeah. Yeah. Audible. Please go ahead.
Hi, Animesh. Hello.
Yeah. We can hear you. You can go ahead.
Okay. So in the Proto-type detector, I mean, I see the inner walls are a bit like gold plated. It looks like gold plated ones. Are there any specific reasons for that? Proto-type.
Oh, why those are look like gold plated?
Yes.
Yeah, yeah.
So it's not gold plated. It's kind of, so these, you see, these are the wire plates.
Wires.
These are the
okay.
wires, and then you have a aluminum kind of shielding all the cryostat. Okay.
Oh, okay.
So these are basically the wire planes. Okay.
Fine.
So you have a frame like here. These are the field cage, and this basically this is, so this you are like looking like a golden, right? So these are the wire planes. You have a frame. You have a three orientations of the wire planes, and these are the aluminum bars for producing the field cage, which covers all the region. That's how you see this looks like a golden one.
Okay. Fine. Yeah. Thank you.
Okay. So just while on this, Animesh, this dual phase TPC. So currently, what is the big success story before you really go with the Proto-type?
So yeah, so the dual phase right now, so they have a built one module like 3x1x1 in smaller,
These are meters,
which is currently finished taking data and did some good job identifying about the mostly the gain. So that's what we are trying to understand about the gain, how much gain we can have from the detector. And for the dual phase Proto-type, right now it's taking the cosmic. So they had right now they are trying to analyze the data, and they will have, they don't have the final results yet because it's kind of delayed, taking data and so on because of some other issues. But it's taking data and tracks and everything looks good.
Okay.
But we are expecting to have the final results. I think soon, maybe in Neutrino we'll have some results, but I'm not sure about that.
Okay.
But and then it will have a beam again when the CERN beam starts. I think in October or November, something like that.
Okay. So the current plan is that your short baseline program at Fermilab will concurrently. I mean, it will continue till the DUNE come up, or
no. So this is independent. This is kind of DUNE and SBN is kind of independent program. But
I know,
but obviously there will be some R&D like that you gain from both from SBN for the DUNE. But it will take data. I believe more than 3 to 4 years. Once it start taking data. And then I think, by that time, DUNE first module might come.
Yeah, exactly. So it is like in some way, until that happens, you will have data coming from this program at Fermilab.
Right.
Okay. Are there any other questions from participants? Okay. So if not, Animesh, we want to again, on behalf of all the participants, we want to thank you once again for taking trouble of able to manage to give this at odd time for you at Chicago. It is almost 7:30, 8 o'clock, and but we wish you all the best on behalf of all of us for all the physics studies as well as your excellent detector building and operation experience, I'm sure, which will go a long way in your career profile. With that, so let us say to everybody, thank you very much for joining. And we will have 2 more lectures, as I said, later this week, one by Professor B.S. Acharya and another one by Professor Patrick Dasgupta on Wednesday and Friday. Please join us back. Until then, thank you very much. And yeah, thanks, Animesh, once again. Take care.
Yeah, thanks.
Bye-bye. Bye, everyone.